Okay, hi guys. So we'll be continuing on seeing more questions on the theory which we have been continuously discussing for the last 2-3 lectures. So let's get started. So the first question is you have to calculate the wave number of radiations emitted from the beta line in case of Baumol series for hydrogen atom. Okay, so calculate wave number. Wave number is this, or 1 upon lambda emitted from beta line in case of Baumol series for hydrogen atom. Okay, so we have for Baumol series we have n1 as 2 and n2 would be, for beta line it would be 4, for alpha it would be 1. We know z for hydrogen atom would be 1. Then we know the Rydberg equation, that r z square 1 upon n1 square minus 1 upon n2 square. So this would give us 1 upon lambda as r z square is 1 upon 4 minus 1 upon 16. So this would give us 1 upon lambda or nu bar as r, then it would be 16. 4 minus 1 would be 3. Okay, so this would be the answer. Next question is you have to calculate total energy, potential energy, kinetic energy of electron from L shell and M shell for Li plus 2. Okay, so for L shell it would be, the total energy would be, we have already discussed it, it would be 13.6. Then it would be nothing but, I hope you all remember the formula for total energy, multiplied by z square upon n square. Okay, so for L shell it would be 13.6, z would be 3, so z square would be 9, n is 2, so n square would be 4, hence this is minus 30.6 electron volts. Okay, what would be the potential energy? Potential energy would be half of total energy. Okay, so it would be nothing but, rather twice of total energy, not half of total energy, it would be twice of total energy. It would be 71.2 electron volt, and kinetic energy would be minus of total energy, it would be 30.6 electron volt. So this was for the L shell. Then for the M shell we have again total energy as minus 13.6, z square upon n square would be again 9. Okay, because for m n is equals to 3. Okay, so it would be minus 13.6 electron volt. Then potential energy would be twice of total energy, so it would be minus 37.2 electron volt, rather 27, not 37. Okay, then we have kinetic energy as minus of total energy, so it would be 13.6 electron volt. So now you have to draw the graphs for these data. Graphs for this data. Okay, so first we have to draw the graph for total energy, which should be on y-axis with z, which should be on x-axis. Z is the atomic number. So we know that as the z increases, as total energy is directly proportional to z square. Okay, So it would be nothing but so let's say with z square we are making, so it would be nothing but total energy would be as the z square increases, so total energy is minus 13.6 into z square upon n square. So let's say at constant or rather not constant n, we would be seeing also the variation of n square as well. Okay, so for this case we'll be first looking at constant n. Okay, so we know that total energy which would be on y-axis would be minus 13.6 z square upon n square. Okay, and z square here, so y equal to, this is m and this is x. So m is this value, okay, and this is in negative. Okay, we are taking m as positive, and so graph would be something like this: total energy here and z square here. So m would be here, slope would be minus 13.6 upon n square. Okay, similarly the second graph which we'll be seeing would be of kinetic energy and z square. So for the kinetic energy, it would be nothing but kinetic energy is actually minus of total energy, so it would be 13.6 upon n square. Okay, so now we can also draw the graph of let's say we have this was the first graph, this was the second graph, and this is the third graph. So for the third graph, let's say we have to draw between r on y-axis and let's say n square on x-axis. Okay, n square on x-axis. So we already know that r is proportional to 1 upon z into n square. Okay, so let's say we are having at constant, so this was at constant n, these two graphs were at constant n. Okay, and now we are drawing the remaining of the graphs at constant z. Okay, so at constant z, what will happen is the slope is obviously 1 over z. Okay, so here we'll be having something like this as the graph. This is r here and this is n square here. Okay, so that would be nothing but y equals to again mx. Okay, so we are taking n square as the x-axis here. So if we are taking n square here, then it's fine, but if we are taking n over here, then the graph would look like something like, so if we are taking n over here, then it would be something like mx square. So the graph would be something like a parabola with slope as 1 upon z. Okay, next if we are taking a look at fourth graph, which is between velocity as y-axis and n as the x-axis, then we know that velocity is proportional to z upon n. Okay, so at constant z, again we are taking this graph into consideration. So if we draw the graph between velocity and 1 upon n, then it would be a straight line and the slope would be z. But if we are taking velocity and n, then the slope would again be z, but the graph would look like something like this. So with this we come to the end of this lecture. Or let's actually see some quick 2-3 questions as well before ending, so that would actually help us to directly move on to ionization energy in the next lecture. So you have to quickly calculate the radius ratio, which is r1 upon r2 of m shell of He plus, which is r1, and between, then second is k shell of Li2 plus, which is r2. Okay, so here again r1 upon r2 would be equal to, as r depends on n square by z, so r1 upon r2 would be n1 upon n2 square into z2 upon z1. Okay, so n1 is 9, rather 3, n2 would be 1 into whole square, and z2 would be 3 and z1 would be 2, so it would be nothing but 27 upon 2. Let's next calculate the velocity of a electron of He plus in meter per second in third orbit. Okay, so again velocity would be equal to nothing but 2.18 into 10 raised to power 6. Then we have z upon n, so z is 2 and n is 3, so we can have 1.45 into 10 raised to power 6 meter per second would be the velocity. Next, let us calculate the ratio of frequency 1 upon frequency 2 of electrons revolving in orbit of hydrogen atom. So again F1 is in second orbit and F2 is in fourth orbit. So F1 upon F2 would be V1 upon V2 into R2 upon R1. Okay, so this is nothing but z square upon n cube, so rather c1 square upon n1 square into n2 cube upon z2 cube. Okay, so that would give us, so z is same for both the cases. Why? Because it is the same atom, so just we have to do n2 upon n1 whole cube, so that would be 2 cube, that would be 8:1. So with this we come to the end of this lecture. In the next lecture we'll be starting off with ionization energy. So till then, good luck and goodbye.